Okay, we're going to start with the simple stuff, and that's calibration. A lot of you have these machines, but it comes to the question a lot of times, how often should I calibrate my machine? Well, there's a quick calibration check that is easy to do on one of these machines, and there's a calibration slug that's screwed in the back of the machine. It'll be sticking out. This is your slug right here. This is what the machine looks like when you turn it on. That's your home screen. You take this slug, screw it in either the left side or the right side of the hub. Press your start button. It says if you wish to do a calibration check, lower the hood and press start. So that's what we're going to do. It's going to spin about 15 or 20 seconds. We'll come up with a number off of that, and we'll also see if our weight placement is correct. So we raise the hood. We roll our weight slug up to 12 o'clock and we get a hammerhead laser beam on there, and then we press K1 for show weights, and I like to see this number 0.08 or less. This machine here we're 0.03, so we're calibrated, we're good to go. If you happen to spin it up and it says calibration required, then you're going to have to calibrate. Anytime you're in a screen that you don't know where you're at, you can hit the reset key twice. That'll take you back home. To get to calibration, I'm going to hit the middle function key here. I get over to calibrate, K1. Then I'm going to do the balancer. It's already highlighted there, so I hit K4 for begin procedure. This is our what we call RFS technology. You read the screen and it tells you exactly what to do. So it says make sure nothing's attached to the spindle, lower the hood and press start. The machine is so quiet you don't even know that it's running. You have to look down there visually to see it. But we'll spin without the weight, and then we're going to spin with the weight on the left-hand side of the hub and then the right-hand side of the hub. So I raise the hood. It tells me to place the cal weight on the left-hand side of the hub and index it to 12 o'clock where my hammerhead laser comes on, and I press K4 for enter 12 o'clock position, and then I lower the hood and press start. It'll spin about 10-15 seconds, and then it's going to tell me to move the weight to the other side. So I move the weight to the outside of the hub. Same thing, lower the hood, press start. This is the final step in the procedure. The third spin takes a little longer. It's about 20-25 seconds, and then we'll be calibrated. There we go. It says calibration is complete. So at that time we go ahead and pull our calibration slug out, and it just goes back in the threads on the back side of the machine. And we put that home, and then we can hit our reset key twice, go back home, and we'll be ready to balance. Alright, we're going to set up the balancer to do a 22.5, which is your normal truck tire that you see everywhere. We're going to throw on our chrome wagon wheel first, and then we use our 219.9 millimeter black disc to center up on the hub. Then we're going to grab our assembly. Roll it up on here. Work our wheel lift. Get our assembly on there. Use our 5-star adapter, get that in our lug holes, wing nut it up. I normally rotate the assembly towards me. 1 or 2 spins, it's transferring weight, and then I use that momentum to tighten up the wing nut. So this is what the balancer looks like when you turn it on. We're going to press K4 for balance. And we've got a steel wheel here, so we need to enter our dimensions. The way you do that is with this inner data set arm, and it shows you on the screen where to hold it for our hammer-on weights. And then I grab the outer data set arm, put it on the other side of the wheel where my weight would go, and then I'm going to tap the pedal with my left foot and enter those dimensions. So right now our load roller is ready to come on, and we'll just lower the hood and press start. You can hear the load roller hit the assembly. That's road testing the assembly and telling us the roundness or out of roundness of the assembly and what we can do with it. It's going to automatically go to the first weight location. The motor takes it there and servo drives and holds it in place. And we're lit up green on the left-hand side here. It's telling us it would want 17 ounces of weight here. This is an excessive assembly that we got here at Michelin. They were using it to show some other things as far as defects in tires. So we would, you would go ahead and hammer on your 17 ounces of weight there, and then you can hit the start button, and it'll roll to the next weight location. And over here we're calling for 18 ounces of weight, and we would put that there. And then if you want to, you can get to the high spot by hitting the button a third time, and that's going to take you to the high spot in that assembly. Now the other thing that we want to look at here is radial runout. This assembly's got an excessive amount of radial runout at 118 thousandths. Normally you're going to see 40, 50, 60, something like that. We know on a steer tire anything over 40 thousandths is going to give us a vibration issue. So what we can do to find out if we can make that any better is I hit the button on the outer data set arm in the home position and get a beep. I bring my inner data set arm under the gutter of the wheel, press the button in my right hand. Now I'm measuring the rim run out, and this is actually electronically separating the wheel and the tire so we can see them individually and identify if we've got a bad wheel, a bad tire, or the two just need to be properly matched to make them more round. So in this case it says we could go from 118 thousandths to 12 to 112. That's not really worth doing, but if you had an assembly that would drop from say 60 thousandths down to 20 thousandths, that would be worth doing. And the way you would do that, you hit the start button, it's going to roll to your location on the tire, and it turns green on the screen here. We've got a hammerhead laser that comes on the right hand side and shows us where to place that mark. So our hammerhead lasers come on, and the screen is showing us to mark the tire near the wheel. So we go ahead and do that with our mark, with our chalk. Now we hit the start button again, and it's going to roll to the wheel location, and we would mark our wheel right there. So now you've got two marks, and we need to pull the valve core out of this assembly, match together on the tire changer, and line those two lines up, and then it'll give you that reduced radial runout. Okay, and you can see on the screen that it's separated the wheel and the tire. That we've got our wheel runout up here that it's got 10 thousandths in it, and the tire runout was actually 123 thousandths. And you can press K4 over here that's show runout plots, and it'll put this assembly, one revolution of the assembly, on a graph, and you can see exactly what's going on with it. The blue is the wheel, and as you can see here, the wheel is pretty straight. The tire has an excessive amount of a high spot and a low spot here, so we can see that our problem in this assembly is the tire. And this one is in such bad shape that we would actually do away with it and get a replacement. And then we also know what our rim average is right here at 10 thousandths. We've got radial first harmonics, which is Hunter's number of figuring out the radial runout, and then TIR is if you put a radial runout gauge on this, which is total indicated runout. So I can hit exit, I can go back to balance. And now let's say we've got an aluminum wheel here and you want to use tape weight. The way you would do that is take the inner data set arm, flip it over upside down, and we hold it in here to the right hand side of your first tape weight location as it shows you on the screen here, and then I tap the pedal and get a beep. And then I'm going to go to the inboard side of the wheel as far as I can, tap the pedal and get a beep. And that's marked my wheels to the point where I've got a tape weight location now. And I can hit the start button and it'll roll down to that first tape weight location. Now you can see the arrows pointing down, and we've got a bottom dead center laser down there to tell us where to place that weight. And once again, the motor is servo driving and holding it there. Now we can also do a rim scan on this assembly if we wanted to. I'll show you how to do that. I'm just going to reset out of this. Press balance. Take our data set arm, move it over upside down, move it to the far inboard side of the wheel, tap the pedal 3 times and hold it. We'll have to retake that. Alright, now I'm going to show you how to do a rim scan. Take the inner data set arm, flip it over, go to the inboard side of the wheel, hold it on the pedal, and now we're doing a rim scan. And you can see on the screen that I'm actually drawing the profile of the wheel with this, and it'll give me an accurate placement of where the best place is to put that weight. Now the function of the load roller, as long as that hand is there, which you can control that by pressing in on the knob here, and that moves him around. Up here you can change from grams to ounces. Down below, that takes the load roller and turns it off. For some reason, if you don't want the load roller on during the balance, you can turn it off manually, or if it's off and you want to turn it back on, you click it back to the left. Okay, also we've got a brown area that rolls on this tire as you rotate your assembly. That is the high spot of the assembly, and you can press the start button and it'll go to that automatically. And your technician can take your chalk and you mark that high spot at 12 o'clock. And if this is a steer tire, you're going to mount it back on the vehicle at 12 o'clock. Through gravity, we got about 175 pound assembly here. It's going to pull down on the hubs and the studs, and you're going to lose some of that radial runout with it bolted in the right location. And then your duals, tells you on the screen here that you want to mark those duals and oppose them from one another, 180, 120, whatever the valve stems allow. And that gives you a more uniform assembly. If you happen to get 2 high spots on a set of duals lined up, you get that eccentric effect. So as soon as you rotate them, cancels that out and gives you a much more round uniform assembly. The vehicle rides better, wears tires better. And we also get the diameter of the assembly. And this one's 40.55, so when matching a set of duals, you know that this size assembly needs to be within a 1/4 inch of one another, side to side, so you can make your marks. And you can put the taller tire on the outside to help pick that inside tire up and shoulder some of the load off of it. And marking these high spots will just totally transform the way vehicles drive.